When we look into what is the shadow pricing, shadow price is the increase in contribution. So by adding one additional unit of the scarce resource, what is the increase in contribution is shadow price. So we have done this particular concept. Going back to our question, we are asked to find out what is the shadow price of these materials would be. So to calculate what is the shadow price, we need to look into what is the contribution which is generated per unit of each of these two products. We have Q1 and Q2 products which are being produced and sold. So we have the selling price and the variable cost and the contribution margin also present. The maximum demand for these products is given, and Q1 has a maximum demand of 500 units per week. So that is a another restriction here. Um, then Q2 has unlimited number of units per week, which can be produced and sold. In such situation, what is the shadow price? Q2 can be sold any number of units, unlimited number, any number of units. So there is no concept of managing with only a limited number of units. But Q1, on the other hand, will be able to sell only 500 units per week. Um, in such situations, what is the selling price of Q1? Let's first put this one as 20. Then from this deduct whatever are the variable costs. One, we have it as direct material, which is 6. Then we have direct labor, which is 4. Then we have variable overhead, which is 2. So the contribution, so this would be 8. 6 plus 4, 10. 10 plus 2 is 12. 12 is deducted from 20, it is 8. Then what is the main limiting factor? If raw material were limited to 2000 kgs per week, only 2000 kgs per week is available. So we would calculate, in case of limiting factors, the decision criteria depends on what is contribution per unit of the limiting factor. So the limiting factor here is material. So what's the consumption of material? So material requirement in kgs. Material used is how many kgs? We see the cost of material per kg is 2 rupees, $2. Cost of material is $2 and the cost comes up to 6. So how many kgs were consumed? Here it would be is equal to 6 divided by 2. That's 3. So when 3 kgs of material was used, we see that the contribution per unit comes up to be as 8. Okay. We are trying to find out what is the shadow price. Shadow price of in this particular situation. Um, the requirement of material would be is equal to 5 divided by 2. So 2.5. The concept of shadow pricing says that in situations where there are constraints, first what we have to understand is what is the contribution which is generated. What is the contribution which is generated in this scenario of a constraint being present? That is one part. The next part of it talks about what would be the contribution per unit of the limiting factor. So every single unit of the limiting factor which is added, what is the increase in the contribution? Now, in case of Q1, Q1 will be able to contribute additional contribution only until it is 500 units. So that is one major drawback here. It would not go on adding more amount of contribution because there is a restriction here. Another restriction is in terms of the demand which is present for Q1. So Q1 will be able to provide additional contribution per unit that has to be calculated. But Q2 will be doing that on an unlimited number of units. So first let's find out what is contribution per kg of raw material. So we got 2.7 for one product and the other one for 3.4. In such situations, now we need to decide about which one is the shadow price. If material were limited to 2000 kgs per week, the shadow price of these materials would be, um, should we go with 2.67 or should we go with 3.4? So what is the additional amount of contribution which is generated by adding one additional unit of the limiting resources? So in that case, 3.4 is the situation and it can go on an unlimited basis. So it would be 3.4. So shadow price is equal to 3.4.
Ma'am,
Yeah.
why we are considering 3.4 as shadow price, ma'am?
Um, one. The point here is what is shadow price for every additional unit of the limiting resource which is added? What is the additional contribution margin which can be generated? So one single unit of material added here, Q1 will be able to give 2.67, but that there is a restriction. It is possible only until 500 units. Next, then Q2 will be able to add 3.4, but any number of units, the same thing would happen. There is no such restriction that it will be only until 500 units. Beyond that, also by adding the number of units, it would be able to take it up. See, 2000 kgs of material. Uh, if I, for let's say for Q1, let's take it as Q1. Q1, if 500 units are used, the material requirement for every single unit is 3 kgs, isn't it? 3 kgs is the material use. So 500 into 3 is 1500. Availability is 2000. Availability is 2000. So when 2000 is available, but if they are only using until 1500 or less than 2000, that is called a slack. So slack is present in case of Q1. It is not a shadow price. Let me put this. Slack or surplus is less than or equal to constant usage or amount available. There is a slack in case of Q1. Okay. But Q2 there is no slack because Q2 there is no such restriction that only 500 units will be sold. So as many as the number of units they want to sell, they will be able to. Because there is unlimited number. Because of this 1500, this is called as this 1500 is less than 2000 kgs of material, which is slack. So there is no concept of shadow price here in case of Q1. I hope I'm clear. Is it clear?
Yes, ma'am.
Okay. So
Ma'am,
then Q2, yeah,
then what about surplus, ma'am?
that is underutilized. Nothing will be done. That is underutilized.
Oh, okay.
The issue is it is not about a product mix. The question is not addressing us about what is the combination of products Q1 and Q2 which have to be produced and sold. Question is not addressing that. So even if that is the situation also, when we see the contribution per unit of the limiting resource, Q2 is better. When the ranking is done, this is 1 and this is 2. So all the all the material will be transferred to the production of Q2 only because Q2 seems to be better and Q2 will be contributing for every single unit a contribution margin of 3.4. So one unit of a material added to Q2, the contribution added is 3.4 per unit. Therefore, shadow price is to connected to 3.4. That is Q2 and which is 3.4.
Okay, ma'am. Now I understood.
The next one, 221. The following details relate to 3 services provided by RST companies. Fee charge to customers. Then we have direct material, labor, variable overhead, fixed overhead. All 3 services use the same type of direct labor, which is paid $25 per hour. The fixed overheads are general fixed overhead that have been absorbed on the basis of machine hours. If direct labor is a scarce resource, the most and the least profitable uses of it are. So we need to find out the ranking part of it has to be done. There are three services. We see service are Okay, so let's we have fee charge. Those details are given. Then we have the direct material, direct labor, variable overhead. So arrive until we have this is 100, this is 150, and this is 160. Then we have direct material, direct labor, then we have variable overhead. So deduct all the three of them, 15, then we have 20, then we have 15. And here 30, 35, 20. Then here we have it as 25, 30, 22. And then find out what is contribution per unit. If direct labor is a scarce resource, so the focus will shift towards direct labor. So how many direct labors are used is the criteria that has to be looked into. Direct labor hours. But how many direct labor hours is not mentioned. The only information what is given is for every 1 hour it is $25 per hour. So if direct labor cost is given as 30, 35, 30, so that is calculated at the rate of 25 and arrived at. So some number of hours and then multiplied into 25, we have the figure as 20, 35 and 30. So now let's find out what are the, how many direct labor hours were used. So here it will be 20 divided by 25. Then we will have it here as 35 divided by 25. Then we have 30 divided by 25. Now find out what is contribution per labor hour. Is equal to, here we have 50 divided by, so most profitable is T and least profitable is S. The following equations have been taken from the plans of dx for the year ending 31st December 20x5. Contribution is given as 12x1 plus 5x2 plus 8x3. So which means that there are three variables. So these variables x1, x2 and x3 um, contributing the contribution at the rate of 12 per unit for x1, 5 per unit for x2 and 8 per unit for x3. When these things are multiplied, the sum total of it should be maximum. So that is the situation here in the objective function about contribution defines it as 12x1 plus 5x2 plus 8x3. Then there are situations which are given. Material which is 2x1 plus 3x2 plus 4x3 when they consume um, the quantity of material which is required by x1 is 2, x2 is 3, x3 is 4. They can use it until 12 kilos of material. Similarly for machine arts also, the total availability is 8,000 machine arts. X1 lies between 0 and 2000. 2000 x1. The x1 is a product which can be produced between 0 and 2000 kgs, not beyond 2000. So that's the restriction. The maximum number of units which can be produced of x1 is 2000. X2, the least production which should be taken up is 100 and between 100 and 500. X3 is between 0 and 200, where X1, X2, X3 are the number of units of products produced and sold. If an unlimited supply of raw material could be obtained at the current price, the product mix that maximizes the value of DXPLC's contribution is unlimited supply of material. So there are two variables which are mentioned here in our question. One is material and one is mesh nuts. So the availability of material, uh, the the usage of material combination is given as 2 units of x1 plus 3 units of x2 plus 4 units of x3 consume. It will require 12,000. But is there a restriction here? There is no restriction. So that is an unlimited supply of raw material. Then what about the other one, mesh nuts? So mesh nuts, there is no such mention that mesh nuts can also be used unlimited number of hours. That is not the case. So if uh, between these two, if material is abundantly available, there is no restriction. Mesh nuts is the only constraint. So what we do is we have to find out what is the contribution per unit of the limiting resource. How do we know what about the contribution? Contribution is mentioned in the objective function, which is 12x1 plus 5x2 plus 8x3. So the contribution per unit of each of these three products is also mentioned. The consumption of mesh nuts is also mentioned here in this equation of about mesh nuts. We have it as 6, 4 and 3. So what can be calculated is what is contribution per unit of mesh nut. So I mean these are the equations which are already framed for linear programming. So from these equations we can draw some conclusion. It looks as if I mean the details which are mentioned about the two variables is given material and mesh nut, but there is a clear cut mention that raw material is not a constraint. It can be there is an unlimited supply of raw material. It can be used as much as it is wanted. So what about the other one? There is no mention, so that is a constraint. So in that case, if we have to find out what is contribution per unit of the limiting factor, so let's take all the three products x1, x2, then x3. We can take the contribution from the objective function, which is 12x1 plus 5x2 plus 8x3. We can also find out what are the mesh nars from the mesh nars equation, which is 6x. I don't know when I got disconnected. I don't know when I got disconnected. Let's see. Contribution is can be taken from the objective function equation, which is 12x1, 5x2, and 8x3. Then mesh nars are 6x1, 4x2, and 3x3. So now what we have to find out is what is contribution per mesh nar, which is equal to, it will be 12 divided by mesh nars. Now we need to find out the product mix. That is what is asked. How many units of each of these products have to be produced so that with the product mix they can maximize their contribution. First, let's rank them. Ranking, X3 seems to be better than the others. X1 is next in the order, and X3 is X2 is third in the order. If X3 is most profitable, so the resources which are available will first be allotted to X3 based on the profitability scenario. Preference would be given because the profit has to be maximized. Profit, if it has to be maximized, um, the resources have to be first allotted to these three products. There are three three equations which are given about the number of units of X1, number of units of X2, and X3 mentioned. X1 can be as low as 0 and as high as 2000. X2, on the other hand, at least 100 units of X2 has to be produced, minimum. Maximum is given as 500. X3 as low as 0, nothing produced is also fine, but the maximum is 200 units which can be produced. Now, what we need to understand is at least 100 is one constant given for X2. So X2 at least, because that's the least preference, because we would not even be considering. But there is also a constant. There is also one limitation here that X2 in any situation should be produced 100 units. So let's take it as 100 units here. Okay. If X2 is produced as 100 X2 for 100 units, because that is the restriction which is already mentioned. If 100 units of X2 are produced, what is the number of mesh nars required by X2? It will be, this is 4x2, 4 into 100. 4 into 100 is equal to is equal to 400. Then comes the most profitable one is X3. So X3 will be given importance. How many units of X3? All the units of what it can produce and sell. The maximum number of units are 200. The maximum number of units of X3 are 200. So it would be the number of hours are 3 into 200. This will be 600. Availability is 8000 mesh nars. Okay. Total number of mesh nuts available are 8,000. So total available hours we have thus 8,000 hours. So if 400 hours are allotted to X2, 600 hours are allotted to X3, remaining number of hours are 7,000 hours. Remaining hours are we have that 7,000 because 8,000 minus 400 and minus 600 is 7,000 hours. These 7,000 hours will be allotted to X1. X1, how many units is the maximum production? 2,000. How many hours does it require? 6 hours each. So here this is 2,000. We see it is 2,000. The number of hours which is required is 6. 2 into 6 is 12,000. But availability is only 7,000 hours. So with 7,000 hours, how many ever units which can be produced, it will be taken up. So remaining hours available for X1. So X1, the calculation would be total availability is 7,000. Each unit requires 6 hours. So how many number of units? Okay, 1,167 units. 1,167 units. So X1 will be 1,167 units, X2 will be 100 units, X3 will be 200 units. So the option C is the correct answer. Answer is C. Including today's class, how many hours of training happened? You have a count, isn't it? The number of hours?
This class until 6 o'clock it will become 40 hours.
40 will be completed, no?
Yes.
So I have asked for another 2 hours for tomorrow also because there is maybe we may not require 2 hours, but then I took 2 hours extra time. We'll have tomorrow also a class because risk and uncertainty also has to be done. We'll do that tomorrow. I mean, if we can start today's class, we will start. Otherwise, we will start tomorrow. 223. It says BJ's company uses 3 components P, Q, and R in its main product. The budget for next year indicates a requirement of 3,000 of each component. The components are all manufactured on the same machine for which only 50,000 hours are available next year. The variable cost of internal manufacture of each component together with the machine hours used are shown in the table below. The table also shows prices quoted by a subcontractor for supplying these components. We have component PQR, Meshnar's per unit, variable cost per unit, subcontractor um, cost, that is dollar per unit. The minimum total cost at which BGS company can obtain the full requirement of the component is. It's it's a combination of linear programming plus make or buy situation, because the component are all manufactured on the same machine for which only 50,000 hours are available next year. The variable cost is given, then with the machine hours are given in the below table. Then apart from that, what are the machine hours per unit? What is the variable cost per unit is given. After that, what is the subcontractor cost per unit is also mentioned. Variable cost is 45, subcontractor price is 65, then 70, then 78, 56, and then 80. So we also have the details about what is the subcontractor cost. If that is the situation, for all the three products, because there's so even if we have to write on a comparative note also, we can still write what is the variable cost and what is the subcontractor's price. Make or buy decision, we discussed that so many times. Make or buy, the decision is between the variable cost and the supplier's price. So that's the decision criteria. So whichever one is lower, the option would be towards either making it or buying it. But here, when we compare that, see, 45 is less than 65, 70 is also less than 78, 56 is also less than 80. So all three components, we see that it is better to make the component rather than buying it from the subcontractor. So that is the important point what has to be. So you can make a note in one simple sentence. For all the three components, cost of making is less than the subcontractor cost. The question is asking us what is the minimum total cost at which BGS company can obtain the full requirement of the component. So we need to find out what is the cost of making all three components. Um, that is the point what we have to look into. But there is also a constraint. The constraint is about the number of mesh nodes. Number of mesh nodes are available only to the extent of 50,000 hours. So 50,000 hours are not sufficient, or whether we just have to check that whether 50,000 hours are available next year will be sufficient for each of them. See here we see the budget for next year indicates a requirement of 3,000 of each component. So if 3,000 uh, units are manufactured, 3,000 into 9 becomes 27, 3,000 into 5 becomes 15, 3,000 into 12 becomes 1236. So all of them added together is definitely greater than 50,000. So mesh nodes required for making the components. For P requires 9 hours. So 3,000 into 9 hours, this becomes 27,000 hours. And the Q 3,000 into 5, which is equal to 15,000, and R 3,000 into 12, which is equal to 36,000 hours. So these are the number of hours which should be available. But are they available to that extent? 78,000. But 78,000 hours are not available. They are only 50,000 hours are available. So in that case, some of them have to be outsourced. Technically, when we speak about which one to be made, it looks like all three of them should be made because the variable cost is less than the subcontractor's cost. But to make all the three of them, we do not this company does not have the required number of mesh nodes. Mesh nodes required is equal to only 78,000. So if only 78,000 hours are available, only mesh nodes available, this is 50,000. Now on account of this, a decision would be to outsource some of the components. But which one to outsource? That is the criteria what has to be looked into. In that case, we don't have selling price, no? Which one of them has to be outsourced? Which one of them have to be made? Generally, the decision is about contribution per unit is the criteria. Variable cost is given, but there is no selling price given. So we cannot proceed in this direction about which one is more profitable direction is not possible. Otherwise, find out what is the contribution per unit, allot these 50,000 hours to the most profitable one, the next profitable one, and the rest of the components should be outsourced. That is the route in which we proceed further. But because selling price per unit is not available, we have to look at the other way around. So the other way around is about the cost which are given. One is variable cost per unit, the other one is subcontractor cost per unit. So what is the additional cost? Which one is most costlier is what we will look into. So let's find out about what is the additional cost of all the three components. P, then we have Q, then we have R. So we have the variable cost. Variable cost is 45, then 70, then 56. Then subcontractors cost 65, then we have 78, then we have 80. If that is the case, what is the additional cost? If it is outsourced, additional cost if outsourced, which will be so 28 and 24. So we have the additional cost if it is outsourced is given. Um, the constraint here is about the mesh nuts. So how many mesh nuts are required per unit? Mesh nuts per unit are 9, 5, and then 2. So if not contribution per unit of the limiting factor, we can find out what is cost per unit of the limiting factor. So let's find out what is additional cost per unit of limiting factor. 20 divided by 9. See, if when it is, uh, if we are to rank them, the least costly one is this one. So if at all, if outsourcing has to be taken up, the least costlier ones will be Q. Then R will be second in number. Then the last preference which would be given will be to P, because it requires additional cost per mesh NAR to the extent of 2.2. That's the highest. But the objective here for us in this question is to minimize the total cost. So the total cost, if it has to be minimized, see, in all situations, we have concluded that cost of making the component is better than making the outsourcing it with the subcontractor. So which one is costing them more if it is outsourced with the subcontractor? P is costing them more if it is outsourced with the subcontractor. So take up the production of P. P, make it in the make it in house, make it in the factory instead of outsourcing. If they outsource it, it would be additional cost for them. That's the highest cost. So why incur highest cost? To keep the cost at its minimum. Um, P P should be manufactured to minimize the total cost. P should be manufactured internally or in-house. Let's see how many hours are required by P. We have already calculated 27,000 hours are required by P. Total hours are 50. Out of that, P will be requiring 27,000. So P will require 27,000 hours. So if P would require 27,000 hours. So remaining hours are that will be 50 minus 27 will be 23 hours, 23,000 hours. The next costlier one is R. R has an additional cost per unit of machinery is 2. So that is next in order. So R should be manufactured, but R availability is 23,000 hours. Requirement is 36,000 hours. We have seen here the calculated one. R requires 36,000 machine hours, but the availability is only 23,000 machine hours. So if only 23,000 machine hours are available, each unit requires 12 machine hours. So out of 23,000 machine hours, how many units can be manufactured? Production of R would be 23,000 hours are available. Each unit requires 12 machine hours. So how many units can be manufactured? 1,970 units. 1,917 units of R will be produced. So what are we asked? The minimum total cost. Total cost only has to be calculated. So the units which will be manufactured for P it is 3,000 units. 3,000 units of P will be produced. 1,917 units of R will be manufactured. Then the remaining requirement, 3,000 units of each of the component is required. So we need to find out what's the total cost. I'll put it here. Is it okay if I put it here? Otherwise, we don't have the question. We would not have the question. Is this fine if I put it here? Side.
Yes, ma'am.
Yes, ma'am.
So the let's find out the total cost. Total cost P would be manufactured. The decision for P is make. The units are 3,000. Cost will be is equal to 3,000 into the variable cost 45. Then R also partly it is made. R make R will be both make and buy. Making is only 1,917. So to make 1,917 units, 1917 into the variable cost is R is 56. How many in total should be made? 3,000. But each of these components should be 3,000 components. That's given in the second line. Okay. So those things also have to be made available. If only 1917 is internally made, the rest of them have to be acquired from the subcontractor. So how many will be acquired from the subcontractor? 3000 minus 1917. So 1083. When 1083 has to be bought, 1083 into the subcontractor's cost is 80. Then coming to Q. Q, all 3000 components will be bought because the meshnars are not available. So the number of units of this particular component is 3000. So all of them will be bought into 78. So the minimum cost, this is the best possible cost which can be arrived at, which is 5. 562,992. That's the cost. 562,992 is the cost. I hope it is clear. I know it's a very long one. Is it clear?
And for this question, we have to round up.
See, rounding up to the nearest thousand it is. So nearest thousand would be, the answer will be 562, 563. 563,000. Any step, any doubt? Otherwise, we'll take up the next question. The next one is a graph. Okay, I'll get the graph also. Um, but actually, we have not plotted any of the constraint. Already built-in question is there. I'll take you to the. I'll just maximize that and then show you because there are so many things which have to be looked into carefully. I'll zoom it to the best possible thing. Of course, we'll go back to the Excel and write the answer there. Not much is there. Mm, See, this is a graphical presentation of linear programming. Linear programming, as many number of constraints are there. Each constraint is equated to the availability and that is plotted on the graph. When the constraints are plotted on the graph, depending on what is the situation, whether it is less than or whether it is more than, that aspect has to be looked into. In that situation, what is done is, if it is less than, from the constraint line, the shaded portion will be taken. It will fall down if it is less than. If it is greater than, it will go above. So that is the point here. There are constraints here. I don't know whether this is clear. Is this clear? Can you see the font clearly? Material B, material A, that part. If it is not clear, I will show this part of it on some other
I can read it.
is it clear?
I can read it. I don't know about this.
Yes, ma'am, for me as well.
Okay, okay. I think little more can also be highlighted. So from the graph, we see that there are constraints. One is about dark material. This is one constraint. There is one material. Then we have material A. Then we have direct labor hours. Then we have mesh hours. So the constraints what we can look into, there are 4 constraints. How do we decide what is the optimal solution? That's the point. How do we decide what is the optimal um, solution is the region which is covered by all of them, all the constraints. So if it is less than, then let's say if it is falling down, if we have the shaded region by material B, if we have vertical lines. Then for material A is this line. So if we put it as horizontal lines, so some way we need to shade these portion. Then for another one which is material A, this one is direct laborers. So maybe twisted line or something like that. If we have the portion shaded, and mesh knot is another constraint. This is mesh knot. Mesh knot is another constraint. So mesh knot maybe a dotted line. Some way you have a dotted line or something like that. So a region which is covered by all of them. This looks all clumsy. The portion which is covered by all the constraints, the area which is covered by all the constraints, okay, that will be taken as the feasible region. So now they have identified a feasible region. The feasible region is represented by A, B, C, D. So all that part of it, shading part of it, which area is covered by all the 4 constraints is looked into. That part is also solved, and that part is presented to us as A, B, C, D. So A is a point. Now the points will be when two constraints intersect. So each one point is one each intersecting point will be considered as one point of the feasible region. A is here, then we have A is here, then we have B here, then C is somewhere here, then D is here. So A, B, C, D, okay, this region has the this is the feasible region. This region has the shaded portion of all the 4 constraints. So we don't have to do anything about it. We have shaded the portion, and they have shaded the portion and identified the feasible region is A, B, C, D. But the entire one big region with so many, there will be so many points in this entire region. There will be so many points. See the points which are created by the intersection of 2 lines will be 1 point. A is the intersection of a line here which is going horizontally and on the y-axis. This is A. B is the intersection of one this vertical line, and there is a slanting line here. So this is a point which is the intersection point of two lines at point B. Point C, we see that the vertical line here intersecting with the x-axis, that is C. D is the intersection of x and y, that is at the origin. After the feasible region is identified, the points of the feasible region are substituted in the objective function. Some objective function C is equal to something would be there. In the previous questions we had 4C1, 4x1 plus something x2 plus 3x2 plus 2x3, something like that was the objective function. So how can they maximize their contribution? So there would be some equation framed. So when these points, intersecting points at which x and y value would be there, when x value and y value are substituted in the objective function, when the objective function is satisfied, that point is called as the optimal point. Okay, so that point is called as the optimal point. I'm reducing the zoom. So the feasible region is given by A, B, C, D. A has intersection of two lines, similarly B, C and D. So the values of x and y at A, B, C, D, all of them individually, when they are substituted in the objective function, the objective function, according to whether it is maximization or minimization, if it can solve the point, solve that objective function, then that point is the optimal solution. That point is called the optimal solution. I do not know whether you've learned linear programming any time. I do not know, but try to understand. If it is still not very clear, I will do it one more time. So the 4 points, the values of the x point, x value and y value at each of these points substituted in the objective function, that should be a maximization or minimization done. After that, but 4 points cannot be, all of them cannot be the solution. Only one among these 4 will be the solution. So which one among these 4 is the solution? Um, whichever point satisfies the objective function. If it is maximization, at whichever point, if it is the optimum, if it is the maximum, that will become. So the question says, the point B marked has been determined to be the point which provides the optimal. So answer is also given. The optimal point is at B. Optimal point is at B. So until that, we have all these things. Let's get back to the Excel. Write something there. Okay. The font is absolutely not clear here. But otherwise also, we see that point B is here. Point B is the optimal. Point is already mentioned here. The point mark B has been determined to be the point which provides the optimal production plan. Which of the following resources will have a shadow price greater than 0? Greater than 0. Tick all that apply. There are 4 constraints: material, um, direct labor hours, material A, material B, mesh hours. When do we have shadow price? When there is no underutilization, shadow price will be whatever is the resource that is utilized to the maximum extent. Every additional unit of the resource which is consumed, um, the additional contribution which is generated is the shadow price. So if there are 4 constraints, in these 4 constraints, which one of them has a shadow price is what has to be mentioned. Okay. the point B, the point mark B has been determined to be the optimal production plan. The production plan that is at its maximum. Fine. If this is the best one, if this is the maximum, because production should be at its maximum. Logically, when we see, it is not a cost that it has to be minimized. It has to be maximized. The more number of units, better is for the company that they can sell and maximize the profit. So it is, in a way, we can understand that that is a maximization function. Optimal production plan, it is a maximization function. If it is a maximization function, there should nothing be underutilized. It should be utilized up till the last unit which is available. There should be no underutilization. All the others would have been underutilized. That's why they were not called as optimal. Optimal is the maximum. Only B is satisfying that maximum number of units of production when it is taken up, which is at X and which is at the point B. Then it is solving the situation. That is the optimal production plan can be taken up. I'll take you to again. This is not at all clear. So B says B is the maximum production at this point. No other point we see that we have A doesn't have, then C doesn't have, D doesn't have. The points at B, when they are substituted in the objective function, the answer is the maximization. Optimal production plan is taken up. All others are above this point. This is the point. All the other constraints have resources starting from here. Okay, this is starting from here, which is above this B. A is also above this point. This constraint A, this constraint A is this is direct labor, which is passing through D. So this is only the one which is equal to the availability. All the others are above that. Okay, which means that they are not making it equal to the optimal point. First one, material B is above that, so there is underutilization. There is no shadow price, but rather there is a slack. So this is material B. Material B is more availability is there, utilization is less. So there is a slack here. Material B is this line. This line is material B. This is also not passing through the optimal point B. It is also not passing through that. So material B also there is a slack. There is no shadow price. And then this one, this slanting line is Mechanards. Mechanards is also not touching the optimal point. It is going above that. So there is underutilization. Therefore, that is also that also doesn't have a shadow price. Now, direct labor hours is touching the optimal point. It is equal to the optimal point. So only this one is passing through that. So therefore, direct labor alone has the shadow price in this particular situation. Theoretically, when we look into that, we understand that it becomes easy. So it is only the direct labor hour which is equal to the optimal point. Optimal point happens at B. At that point, only direct labor hour is becoming equal to the optimal solution. So utilizing to the optimum extent, all the others have resources above this, and the utilization would be only till the optimal point. So for all the other three constraints, there is slack. Only for direct labor hours, the shadow price is greater than or equal to 0. So in this case, Direct labor alone has shadow price. I don't know how much is it clear. Please also read the study text, because linear programming overnight to get that is also not possible. It takes some time to understand the linear programming concept of it. We have no such questions about me plotting them on the graph things. Therefore, for you to understand, um, I do not know anything beyond that to say.
Ma'am?
Yeah.
Ma'am, I have a doubt in that graph, ma'am.
Yeah.
If a constraint if a constraint passes below the optimal solution, that would be under utilized of the
No, no,
resources
it
or over,
cannot
ma'am.
go below the optimal solution, because the feasible region, when it is decided, the feasible region um, cannot be a region above one constraint, because the shaded, let's say that, for example, let's say a constraint is somewhere like this. Okay, this is one constraint. Optimal point will not be here. Optimal point will be okay, something like that. From here, then here, then so whatever are the intersecting points, this is also this one and 0. So this will be the, so no constraint will go below the optimal point. Optimal point is the limit there. If it is, if any other constraint is passing below that, then we check uh, that is not the optimal point. To ensure that, there is a concept called as ISO contribution line. In fact, this is an ISO contribution line to verify whether there is any other point which is below the optimal point which satisfies the objective function. Um, Let me put you to the other image. See, there is a line here, dotted line. This is called as ISO contribution line. So what do they do is, parallel to this optimal point, they draw a line and keep testing. They keep moving it in all possible direction, but parallel to the point below the optimal point. They keep running a line and then verify whether any other region below the optimal point can satisfy the objective function. This is not a constant, this is a dotted line. It is to test whether there is any other point below the optimal point which can satisfy the objective function. To verify that, this is done. So they keep moving this one other any direction and then test about the points and substitute in the objective function. So there can be no constraint which goes below the objective optimal solution, which cannot be below the optimal solution.
Okay, ma'am.
Then we'll do the next one, 225. The following details relate to ready meals that are prepared by a food processing company. K, L, and M are the three different types of meals. Selling price, ingredient, variable conversion cost, fixed conversion cost, profit, oven time, oven time, minutes per ready meal. The fixed conversion costs are general fixed costs that are not specific to any type of ready meal. Each of these meals is prepared using a series of processes, one of which involves cooking the ingredients in a large oven. The availability of cooking time in the oven is limited, and because each of the meals requires cooking at different oven temperature, it is not possible to cook more than one of the meals in the oven at the same time. The most and the least profitable use of the oven. Oven time is the deciding factor. Um, first, First arrive at what is contribution margin per unit. 225. There are three different types of meals. Okay, we have L, then we have M. The selling price is given, then the costs are given. The variable costs are first we have ingredients, then we have variable conversion cost, that's it. So ingredient cost is 2, 1, then 1.3. Then variable conversion cost is 1.6, then 0.80, then 1.85. That's it. Find out what is contribution. What is the oven time? Oven time is given to us as 10 minutes, 4 minutes, 8 minutes. So contribution per oven time. Per minute of oven time, 1.4 divided by rank them. This will be 1.3, no? This will be 0.2 and this will rank 3. So most profitable is L. Then we see least profitable will be K. JRL manufactures two products from different combinations of the same resources. Unit selling prices and unit cost details for each of the products are given below. J and L are two products. We have selling price, material A, B, skilled labor, variable overhead, and fixed overhead. Which of the following equations represents the ISO contribution line? So there is a contribution line which is meant. I'm sorry. There is an objective function which is mentioned by an equation. M is equal to. There are various options which are given. So the contribution part of it from J and L. See, the number of units are given as 13 and 11 multiplied into the contribution of J and L. Like that, we have to verify in all of these four equations. Which one is correct is we do not know. So which of the following equations represents the ISO contribution line? So that is the point. First, what we need to understand is identify what is the contribution which is earned for each of these products G and L. Let's just put this one 227. We have J and L. Selling price is given 115 and then 120. Then we have direct material A. This is 20 and this is 10. Then we have direct material B. This is 12 and this is 24. Then we have skilled labor, skilled labor 28 and 21. Then we have variable overhead which is given as 14 and 18. So then we have contribution. Contribution is equal to we know what is the contribution. Now what have we to do? We just have to substitute this contribution per unit in each of these four alternatives A, B, and C, and then check whether which one has the point at its maximum. So option A. So A talks about M is equal to 13 into for J it is 41 plus 11 into 47. Check how much does it come up to. I think I made a mistake. Which of the following equations represents the ISO contribution line? Not about maximization. It is about ISO contribution. I'm sorry. Sorry about that calculation. That calculation, if we calculate that, we are just verifying what is the objective function. But the question is not asking about, see, if we do this one, we are just verifying about at which point M is maximum or minimum. That is the calculation. The question uh, the question is asking us about what is the ISO at which of the equations represent the ISO contribution line. See here in this case, of ISO contribution line, um, see this one goes parallel. ISO contribution line goes parallel to the optimal solution. So the values of x and y will be the same because it is parallel. So the value of J and L, if they are 41 and 47, that is the ISO contribution line. How many number of units, various number of units of X and Y, J and L substituted is tested, but it is only about the ISO contribution line. So if it is only about the ISO contribution line, we just have to verify how much of contribution of J, how much of contribution of L is to be there. So I'm really sorry I made you do the additional work. That calculation is most suitable when we are trying to solve whether this can substitute it. This can solve the objective function. But objective function is not the question. It is only the ISO contribution line. So wherever it is 41 and 47, that is the so B is the answer.
Ma'am, what is the meaning of ISO contribution line?
What is the purpose of it? The purpose
And
of
in
it.
general, the purpose and the meaning.
The purpose of it is, see, we have you also have asked a question that what if there is a line which comes below the optimal line. See, there may be a possibility is what has to be verified. If it has to be verified, maybe there is some point below the optimal point or some other place in that feasible region. So there might be something else, some other point which can solve the objective function. So for that reason, putting that optimal point and drawing a line. So it is not only at one point of time. So they keep moving the ISO solution, ISO contribution line. It is now here. So next time they just slightly move it above. So something like this. At this point again they verify. So they keep changing like that, a parallel line to the optimal point. So they keep verifying that. So the values of x and y, the coefficients would be the same because they are all parallel to the um, optimal solution. So they keep moving that. So to test whether any other region in this feasible portion, feasible region can satisfy the objective function. That is the purpose. So every variable of x and y will have the same coefficient. Only the values of x and y will keep changing because they run parallelly. That is the point of ISO contribution line. Um, See, these are simple concepts, but not very commonly available in the textbooks and all. So, any such thing which you feel that you're clear with that, but you're yet not clear. See, we have a static thing wherein we keep writing, scribbling on that. Um, a video would be much clearer to understand. See, ISO contribution, all of a sudden, this concept has come up. So we do not know how to be figure it out. So you can watch some videos which are there on YouTube. You should also have the practice. You should learn the habit of watching various videos on different topics. So maybe This time you look at any video, go to YouTube and type ISO contribution line. So somebody must have explained it with a video. That would be much clearer. Of course, we are also using technology, but unless I scribble something on that, it is not um, seen here. So it is kind of a static situation only. Those are pictorial and graphical, and then images, and then film running. That makes things much clearer. Please watch some video on ISO contribution line if it is not still not clear. Um, how much time? 15 minutes time is there. Let's see, as much as we can do, we'll do that. Graphs, we'll take it up tomorrow. This 228 is a graph. Limited time. Whatever we can do, we'll take it up. 229, I'm putting it here first. Tomorrow also, there's a lot of work which is there. Risk and uncertainty, in one day I have to finish it. The initial topics had less questions, so my estimation was this is the first time I'm doing P1, so my estimation was not correct. I thought few questions would be there. So, but then the number of questions which are covered in all of them are many questions are there. So my estimation went wrong. See, if it doesn't end in tomorrow's session also, I can also request for another class. So don't have to be worried about that. Question number 229. Contribution is given as 12A plus 8B, where A is equal to number of units of A and B is for product B. Then a graph has been identified that the optimal production plan exists at a point where the following two constraints cross. Material X is given as A plus 2B is less than or equal to 8,000. 2A plus B is less than or equal to 13,000. There is a maximum demand of 10,000 units of each product. I think we've done a question like this. How many units of product A are produced in order to maximize contribution? If I'm not wrong, we've done a question on this one. This one. Isn't it? Contribution is 6A plus 4B. The details are different. Contribution is 12A plus 8B. Here the contribution is 6A plus 4B. The rest of it is same. Just equate them and eliminate one unknown variable and then substitute that in the equation to find out what is the answer. So I will write, because we are short of the time, I will not do 229 here because we've done a similar question here. Two 31 also is a similar one. Please look into this one. Contribution is given as 5x plus 10y, product x, product y. There are two things which are given. Maximum demand is 12,000. First equate them. 6x plus 4y is equal to 62,000. 2x plus 5y is equal to 50,000. Eliminate one unknown variable. Then find out what is the other. Substitute this one in the equation. So that is okay. So that will be the end. There are graphs. We'll just look into the graphs. What is that they are asking? Two graphs are there. If we do these two graphs, that would be the end of this topic. From here only we'll see. An organization has created the following linear programming solution to represent the position it faces currently in the presence of short-term scarce resources. The feasible region is given as A, B, C, D. The organization manufactures two products, T and R. Each T requires 1.4 kgs of material A and each R requires 2 kgs of material A. The maximum amount of material A available is dash kgs. B is the point which is maximum material. Help me out with this figure. The organization manufactures two products T and R. Each T requires 1.4 kg. T is here, R is here. Okay. Okay. T we see R is equal to 500. I was not able to figure it out. So the image when it is made big, so there are manufacturing two products. One is R, another one is T. Optimal solution, optimal point, we already understood that it is at B. Okay. At B, T is equal to 800, which is already given, but we do not see T touching optimal solution. See, the T value is at 800, but T is not touching B at all. So T is equal to 0. R touches B at this point. Okay. So it is only R which can be manufactured. T is not even passing through the optimal point. So when that is not passing through the optimal point, I will reduce the.
How can they be parallel lines? Shouldn't if it says that 1.4 kg or some material
Requirement is, this is the requirement. Requirement is that, so T requires 1.4 kgs of material A, but the production of T will not be taken up because T is not passing through the optimal solution. So even without producing any number of units of T also, they can arrive at the optimal solution. See, some of the questions we have checked that some of the products are not taken up at all because the resources are not available. They are not produced at all. If they are produced, it will require 1.4 kgs. But they are right now not considering producing T because that's not passing through the optimal point. They would not produce it. They will only take up the production of product R. R requires 2 kgs of material A. So 1 unit requires 2 kg. So how much? So what is that we are asked? We are asked to find out what is the maximum amount of.
If in the question the parallel lines is what's the requirement, then what are the axes? Why are the axes T and R?
T is a parallel line to x-axis. R is a parallel line to y-axis. We can have.
Yes, ma'am, but the y-axis is called T and the x-axis called R.
No. These are not the axes. These are two products. So the products are given. These are two the output, if they take up, they are considering the production of the output as R would be 500 units and T would be 800 units. That is what they are taking it up. Okay.
Okay.
So in that case, in that situation, they have planned it such a way. But then, if they take up the production of these two things, that is R 500 and T 800, they are not reaching the optimal solution because maybe some other constraint is present there which will not allow them to take up the production of one of the products. So T, because it is not touching the optimal point, it will not be considered. But R is touching the optimal point, so only R will be taken up. And R requires 2 kgs of material A. Okay, R requires 2 kgs of material A. Therefore, 2 into 500. I'm still not material A, material A, material A. Okay. Let me look into that and then get back to you tomorrow. It's already time. That is one graph. One more graph is also there. So these are the two graphs which are there. That's it. We are through with these two graphs. I'll talk about them tomorrow. So the last topic what we have is risk and uncertainty in the short run. So that we'll take it up in tomorrow's class. Okay. We will try to wind it up tomorrow. If I do not know how much time they would take, there seems to be many questions. If we cannot finish it in tomorrow's class, in that situation, I will also request for another additional class. But whatever are the questions, we will try to end it up in tomorrow's class. Okay, is that fine?
Okay.
Okay.
Okay, ma'am.
Good day then.
Thank you.
Thank you, ma'am.
Okay.